Welcome everybody for this new webinar, and I let Professor Rafiq Agesh to introduce the speaker today, Cyril Banderier.
Thank you, Nabil. Hello everybody. We have the pleasure today to have with us Dr. Cyril Banderier from the University of Paris North, France. Cyril Banderier is a senior researcher at the University Sorbonne, Paris North. He got his PhD thesis under the supervision of Philippe Flageolet at INRIA in 2001. Since he wrote more than 70 papers applying the techniques of enumeration and asymptotics of combinatorial structure to trees permutation, words, random graphs, random walks, errors, etc. His collaboration with Hussein K. Huang in Taiwan was rewarded by an international award of the Académie des Sciences in 2030. The fields of interest of Cyril are analytic combinatorics, probability theory, number theory, analysis of algorithms, computer algebra. The talk of Cyril Banderier today is with title Periodic Polya Errors, the density method and asymptotics of Young tableau. Thank you again, Cyril, and you can start, please.
Okay, thank you, Rafiq, and thank you all for the invitation at this seminar. So first, do you see my full screen here?
Yes.
Okay. So indeed, during this talk, I will consider some combinatorial objects which are related at the same time to urns, Polya urns, and to Young tableaus. And we will explain these two objects a little bit later. So this is a joint work with these two guys, Michel Wallner, who is currently a postdoc at the TU Wien, Technische Universität Wien, and my colleague Philippe Marchal from the University of Paris North. So I am in the computer science lab and Philippe in the mathematical lab. And for those of you who may wonder, there is a big tradition in France that combinatorics is in computer science. And it has a lot of applications to computer science, as we will see. So this work is based on the article that we published last year in Annals of Probability. And there have been since a little bit follow-up of this work that possibly I will mention en passant. So the first big tool to mention that we will use is analytic combinatorics.
Look at him. Combinatorics.
Yes. Rafiq, can you close the mics of everybody? Not me. Well, also.
Oui, Nabil, tu peux fermer les micros.
Classical joke. Join.
Okay, c'est fait, c'est fait.
Okay, so the main tools will be analytic combinatorics. So it's a field which is a kind of unification of ideas of Euler and Cauchy. Euler was one of the first big user of generating functions, and Cauchy for the complex analysis. And there was a renewal of those ideas in computer science and for analysis of combinatorial discrete objects by Knuth in the Art of Computer Programming, which is considered as the Bible for people in theoretical computer science. And all of this was even further developed from the 70s, 80s, 90s, and so on by Philippe Flageolet. And when we mention combinatorics, in fact, it could really be combinatorics with S, because there is a lot of different subparts of combinatorics. It could be to do enumerations, to do bijections, to analyze the algebraic structures of algebra and so on, additive combinatorics, topology, some geometrical combinatorics, extremal combinatorics à la R2, additive combinatorics. Oh, additive is twice, big addition. Combinatorics on words and so on. So but for, I would say, all of them, in fact, the analytic combinatorics could play a role in the following sense. So whenever we aim to analyze objects which have a given size, we can want to make the inversion of the number of objects of a given size. So those objects, they will be typically recursive structures. And we can want also to establish their statistical behavior. So the tool will be to use some generating functions. So AN will be the number of objects of size n. Okay. And we go like this from the discrete world, objects of size n, to the continuous world, a power series that we can consider as the function in the complex plane. Then we apply some analysis. Alors, there was this Bourbaki definition of analysis, which is majoré, minoré, approché. So it was by Dieudonné. And on those generative functions, we will have some functional equations, and then we can solve them, find some closed forms. And then we can analyze their singularities in the complex plane to use methods like saddle point methods, Mellin transform, and so on. So it's asymptotics. And those asymptotics are describing some possible limit laws of the object and so on. So you get back to some properties of the initial discrete objects. And you have applications for sure, rhetorics, computer science, probability theory, as we shall see also, number theory, biology, biology, chemistry, statistical mechanics, and a lot of other fields also, whenever you have these combinatorial structures in the background. And here, one important credo was the motto of Fussenberger, that whenever you have combinatorial identities between combinatorial structures, relating combinatorial structures, then you can translate it into a functional identity. So you can see it also like to go from the non-commutative world to the commutative world. So this is well summarized by the Flageolet symbolics approach, which has some traces partially in a lot of your works. It was not fully created by Flageolet, but I would say it was unified and further developed by Flageolet and applied to a lot of examples. So whenever you have some generating functions containing some objects, then, for example, you could have some objects of type A and some objects of type B, and then you construct all the pairs of objects. One guy is from A, one guy is from B, and the Cartesian product like this. And then the generating function of this Cartesian product is just the product of the generating function. And if you consider this property, you will prove that if you consider tuples of any length, it will be this, because it is 1 plus 1 plus A plus A squared plus A squared and so on. So it's just an application of the previous one and the union in one sense. And you have a lot of other constructions that you can do on atoms of your combinatorial objects, bigger objects. You can put them in sets, in cycles, to substitute some atoms by some bigger stuff and so on. And all those combinatorial constructions, you see, they translate into some functional identities. And sometimes they give some very short and elegant proof. For example, the inclusion exclusion, it will be just to do this substitution in generating function. Or you can also read it backwards and the z minus 1 if you want. So if you relate the function in the other direction. One interesting example that we will use also is that if you have some object of size n, okay, you have n atoms, and you are pointing one of the atoms. So from one object of size n, you get n copy of it depending on which atom you point. Okay, and this, it is just the derivation multiplied by z. Why? Because if you apply this to some objects of size n, so you can see, for example, instead of az, you take z to the n, and you apply this to it, you get n times Cn. From one object, you get n copy. So like this, it's very trivial, stupid, and so on, but you will see the full power of this very trivial ID later. Okay, and this gives very fast proofs of the Taylor formula, the Lagrange inversion formula. It explains also why Hopf algebra, for example, leads to identities and so on. And all of this, we have examples later, nonsense. And also something which is noteworthy is that all of this, you can automatize it with some tools of computer algebra or softwares like Maple or SageMath or so on. Okay, so let me give one example. Do you see the black bars that I have on the title, or I am the only one to see it? I have some Skype stuff here, and I don't know if you see it. If you don't see it, if you don't know, it means that you don't see it. Okay. It's some Skype menu which is hiding my slides for me, not okay. For you. Okay. So I don't see the title of my slides. So, so we can begin with the first example of this magic dictionary, of this symbolic dictionary, a very trivial one, which is counting binary trees. Okay, so binary trees, you have a recursive definition, which is that a binary tree is either a leaf or some internal node to which you attach two binary trees. You have a Cartesian product here and a union with a leaf. If you apply the dictionary, you just get this functional equation that you can solve. You get this closed form. And if you do a Taylor expansion of this function, you would get, for example, that you have 14 trees with 4 internal nodes. And for sure, if you apply Lagrange inversion on this or many other possibilities, you will get closed forms for the coefficients, which are the Catalan numbers. And if you apply Stirling on this expression, you get that the asymptotics is 4 to the n divided by square root of pi n to the cube. You have other ways to get this asymptotics, which is just also to see that the singularity of this function. So 0 is not a singularity because it's 0 divided by 0 is singularized. It goes to 1 when z goes to 0. So the true singularity is 1 over 4. So therefore, by the Hadamard theorem, you know that the coefficient will grow like 1 over 4 the inverse of the reduced, which is 1 over 4, which is 4 to the n. Okay. And if you do more precise local analysis, because of the fact that you have it behaves like a square root near the dominant singularity, then you will get the square root of pi n to the cube. Okay, this is called singularity analysis, and you have also other ways to get this asymptotics. But why I am mentioning this? Because you don't always have the closed form for the coefficients, but the singularity analysis on algebraic functions, you will always be able to perform it. Okay, so now just a simple variation of it. If you want to analyze the average or the typical height of your tree, okay, you consider trees of size n, uniform distribution among them. What is their typical height? Okay, so then you can consider this relationship: a tree of size of height at most h plus 1. It's what? It's either a leaf or a pair of trees of size at most of height at most h. Okay, and here I am counting no more the internal nodes like above, but here I decide to count the leaf, the number of leaves. Okay, and when you do this, in fact, you recognize exactly the definition of the recursion of the Mandelbrot fractal, which is this one. If you start from some initial value z, and you iterate this relation, it will converge or it will diverge. And the speed of divergence, you put some color with respect to the speed of it, and then you get exactly this famous fractal. And here you have the 1 over 4 singularity. Okay, and then if I want to get the average height, I can compute the cumulative height of trees. So this is just given by, okay, I take the sum of all trees, and I subtract those exactly of size at most h. Okay, so this is the cumulative height. You can check this fact, it's quite easy. And then, if you do some singularity analysis on this guy, you can prove that locally it is behaving like some log of 1 minus 4z, okay, near the singularity 1/4. And then by singularity analysis, you get that the coefficients behaves like 4 to the n divided by n times the constant 2. Okay, and then if you do the constant of the cumulative height by the number of binary trees, you get that the typical average height is 2 times square root of pi n. And what is nice is, in fact, is that you have some universality here. Instead of taking binary trees, you could add ici some bh to the cube, b to the fourth, and so on, to have a full distribution over any number of children. And you can even put some probabilities to have 2 or 3 or 4 children. Then you are exactly in the model of the Galton-Watson trees. And like this, you are proving that for all those different families of trees, in fact, you behave like square root of pi n times some constant, which depends on the distribution of the number of children. And you can even do more by looking at the moments. For example, you will get a limit law, which is here related to the Jacobi zeta function. And this is universal for all these simple families of trees. Okay, very classical application of analytic combinatorics. Let me give a last application of classical application of analytic combinatorics, which is to analyze permutations. So a permutation, you can see it as a set of cycles. Okay? And if you do this, what you get, cycle, it's we saw it in the magical dictionary before, it's log of 1 divided by 1 minus blah, 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 so atoms, okay? And set of is exponential. And if I am marking the number of cycles, it's exponential of u times the generating function of cycles. So this is the generating function. Okay, and now if I want to compute the average number of cycles, I just compute this quantity. It will give me the average number of cycles. And this quantity is nothing else than the derivative of this function at u equals 1. By this notation, I means I am extracting the coefficient of z to the n by n factorial into this quantity. Okay. So computing the mean, it's just taking the derivative at u equals 1. Okay, and if you do this, then you get this quantity. Okay, and the coefficient of z to the n in this is 1/n. When you multiply by 1 divided by 1 minus n, you do the partial sum. So it's the sum of the 1/n. This is the harmonic number. So it's hn, the harmonic number. And the asymptotic of them, it's well known. It's log n plus Euler gamma constant and so on. So you get directly like this. That's an average number of cycles. It's log n plus this. But you can do more. You can follow the fluctuations. You can get to the standard deviation, which is like this, and the fluctuations, which are then of Gaussian type. You get a Gaussian limit law for the average number of cycles. So this is an extension of the Erdős-Katz theorem to many structures. For example, Erdős-Katz also did this for prime numbers, but you can do it for example, if you consider the number of factors of polynomials in the finite fields, okay, you will have the same limit law. And in fact, you have it also for, instead of taking polynomials in finite fields, you can consider some different ideals and so on. And you have some abstract notion of the full generality in which it works, in one sense, in this book, Abstract Number Theory by Knopfmacher. Okay, and a funny application of these ways to do counting with respect to permutations. This is the 100 prisoners problem, in which, well, I will come back to it at the end if there is occasion, if someone is not knowing it and so on. But it's, I I put a link here in the slide, so you can get the slide after, and you can read the problem, and then you can try to think in which way to use this to solve the problem. It's a striking problem and striking solution. Okay, so now that you are all familiar with analytic combinatorics, we will apply it to Polya urns. So first, what is a Polya urn? Here you can see George Polya, George Pouya, in Hungarian, we should say. Okay, so it is an urn which contains some balls with some replacement rules. So in the urns, you have balls of different colors, for example, here, white and black, and you will pick at random one ball in the urn. And if you pick a black one, you will apply this rule. I pick a black ball, okay, so I put back the black ball, okay, and I am adding these two guys. Put back the black ball, and I am adding this, okay. Now, if I pick a new ball at random, okay, and it's a white one, okay, so then the rule says that, okay, I put it back, and I am adding these two stuff. Okay, and I go on. I pick a ball at random, and oh, it's a white one. I put it back, and I am adding two white, and so on. So you iterate this process. You iterate this process as long as you wish, and then the natural question is what is the number of the distribution of the black balls after n replacements. Okay. So the full model is described by what? It's described by a matrix, okay, which is saying that whenever you pick a color, you replace it by this number of balls of this color and this number of balls of this color, okay? So in this case, it can be modeled by a 2x2 matrix, okay? And therefore, coefficients here are integers. In the example that I considered, there was a property which is playing a role, but you could do without it also, which is that the urn is balanced, which means that I was always adding the same number of balls at each unit of time. Okay, for sure the proportion was not the same, but A and B or C and D, not the same, but the number of balls, which means that at the time n, the number of balls is deterministic. It's exactly this number, the number of initial balls plus the number of initial white balls plus k times the number of steps. This is my number of balls at times n. But the distribution is completely random. It depends really on what I have picked in each steps. Okay, alors you have already a lot of natural models. For example, this is the first model considered by Polya, and also his PhD student for the contagion processes, disease, and so on. You have some different type of urns which were analyzed by different type of people, and also some famous problems like the coupon collector problems can be modelized as a urn process. Okay, the first analysis of Polya urns was indeed by Polya and his student also Banderier, in which they analyze this type of urns. You have some very funny applications of urn models. For example, Rejust, which is the guy from the RSA crypto system, did use urns to check if you can trust the results of elections, or to be sure that your vote was counted, or to increase the probability to be sure. So you can check his article. It was also used, for example, in some funny algorithms for de-anonymizations in Bitcoin, so the crypto money in peer-to-peer network. It was applied, for example, to MRE trees, to branching processes. Instead of having some integers, you can put some random entries in it. So you have some articles biographic on this. And you can use also a lot of different tools by probability theory or even analysis. Martingales, contraction methods, approximation to analyze all of this. You have many experts on this for sure. And you have many generalization of it. You could add more colors. You could, instead of picking one ball, you can put several ones at the same time. What happens if when you put some negative entries, when you remove more, when the rule is saying to remove more than what you add, so you could play with the time to be non-Musician times. So all of this is leading to more and more complex types of Follier urns, and not everything is solved. Okay. So in this work, we will consider the following extension of Follier urns, which will be at each unit of time, we will consider a replacement rule, which is depending on the parity mode P, not the parity, but the P arity. We will consider it mode P. So in each residue classes of P, mode P, we will have the same rule. So it will be regular or periodic replacement rules. So we can keep exactly the same definition of balance as before. If the sums of the lines is the same, it's called balanced. Okay, so let me give an example of a periodic Follier urns of period 2, and we will call it the Young Follier. So for each odd unit of time, for each odd step, we will apply this rule, this distribution rule, while for each time which is even, we will apply this substitution rule. Okay? And just a small warning, if you try to modelize it as a classical Follier urn, even with multi-drawing, you cannot do it. Okay, so it's really a new model by itself. And for example, here is what it gives. If we start with one black ball and one white ball, okay, so the time here is even, so we apply the rules for even time. So we get this substitution, this matrix substitution, and at odd time, we apply the matrix for odd times, which is so this one, oops, okay. And this is summarizing the different histories, the different possible evolutions of the urn. And you see that, for example, at time 1, all the possible compositions of the urns are either this one or this one, and with a weight one. There's a number of ways to access to it. And here you see that in this case, this one with weight 1, if I take a white ball, I am reaching this composition, and this stuff, if I pick a black ball, I am reaching the same stuff. So in this case, this new composition will occur with a multiplicity which is 1 plus 1. Okay. So this is the way to explain the stuff here. And let's use this example, which is perhaps more interesting. In this case here, if I take a white ball, I can pick this one or this one or this one. Okay, so it gives me 6. And if I take a black ball here, I am reaching here also, but here I have only one choice. So the total weight of this configuration will be the 2 plus 2 plus 2 here, plus 2 here, so 8. Okay, so now you should understand this picture. And this is therefore just a polynomial which is encoding all the possible distributions at times n, at times 3 here. And then I do a generating function of this, And I get what we call the generating function of histories, which is encoding all the distributions at any time. Okay, so now how to get the exact distribution at times n and the asymptotic distribution. So for the polyhedron model before, so the generating function, for example, is starting like this, or it is evolving when n goes to infinity, when the time here goes to infinity. First, it should be said that you could have, depending on the urns, a lot of different models. For example, in some previous works, sometimes you get the uniform distribution, the normal distribution, the beta distribution. All of them are classical limiting distributions for the composition of urns. Okay. In your case, the limit that we will get is related to the generalized gamma distribution. Alors is French. So, so this distribution is depending on two parameters, two real numbers, alpha and beta. And it is, in fact, can be seen as also as the distribution of gamma distributed variable to some power. It will give the same density. Okay? And here, depending on some different values on the alpha and so on, you have some different plots here. And the polyhedron model, in fact, is this one. Okay, so how to get this result? So the exact claim first is that the number of black balls renormalized by this quantity, converging to this generalized gamma distribution. So first, it should be said that this limit law, it's not easy to guess. For example, if you consider the matrix which is used at odd times, it is this one, and the limiting distribution for it will be, if you apply it everywhere, will be the uniform distribution. If you apply the matrix of odd times everywhere, then you will get the half normal distribution for the urns. And what we do a mixture of both of them at odd and even time. And this is leading to this distribution. And I claim that there is no easy probabilistic way to directly do a kind of mixture of these two stuff to get that it will be this one. So how to get these results? So we will use the generating function of histories. And for sure, because we have some different behaviors at odd time and even time, I will introduce the generating functions of histories at even time and odd times, okay, which is this. And then what happens? The dynamic of the process at odd times is encoding by this operator. Why? Here I am saying that if I pick some balls which are counted by x, okay, I am adding 1. So, which means what? Which means that if I have some x to the n, I want to get n times x to the n plus 1. And this is exactly what is doing this operator. And now for the stuff counting by y, it will be the same. Here, for example, if I take this one, whenever I am picking this color, I will get 2 of this color. And therefore, I get from y n, I want to get n times y n plus 2. This is exactly what is doing by this operator. Okay. So therefore, the dynamic of the process is the evolution in time of odd ones it is just I am applying this operator at even time. And the evolution of time, if I do one step of the process on the even time, it is just applying this differential operator to the odd time. Okay. So if I do this, and if I remember that the number of balls after one step is deterministic and counted by this, I get a system of differential equations, of partial differential equations. And I will have some derivative with respect to x, to y, to z. Ooh, so not easy to solve. But you can indeed work with it, and you can eliminate some variables and do some substitutions using a little bit of the definitions of the models. And then you get a simpler differential equation, which is this one, a little bit simpler. It's still a partial differential equation, okay? And here, what could be said? It is already quite noteworthy that there is this x minus 1 factor here, okay? And it plays a role into the proof of the next lemma in one sense. And because when we do some substitution by x equals 1 or stuff like this is cancelling. And in fact, this system of partial differential equations could be transformed into a single linear differential equation with only one derivative. With derivatives with respect to only one variable, which means that the geometric motions are definite. So what is this notion of definite stuff? This is exactly the set of functions which satisfy differential equations with linear differential equations, finite order, with coefficients which are polynomials into the variables. Okay. We'll give the example just after, but just to convince you that it is quite an important word, it is appearing in a lot of different fields, and you have all these very nice books which are dedicated to it. So to play the mathematics which are behind the definite functions, sometimes it is also called holonomy theory. The definite functions, they are sometimes also called holonomic. And they are the key ways to handle sums, integrals, special functions. So for example, the books which was the most sold in the history of mathematics was this Handbook of Mathematical Functions by Abramowitz and Stegun, because it was for sure also used by some more applied mathematicians in physics, engineers, and so on. So it is big books with a lot of tables, values related to special functions. Special functions is mostly a keyword for functions which satisfy the differential equation. A noteworthy differential equation. It's functions which satisfy such a differential equations which are a priori not easy to express in terms of simpler functions. So therefore, we needed some name to them, so you can think the Bessel function or stuff like that. Orthogonal polynomials, Q-series, all of this in the world of definite functions. And it allows to get identities, asymptotic functions, exact numerical values, some structural properties. And it plays a role in combinatorics, in computer science. You can see, for example, well, I will say you have a lot of examples of this in the book by Flageolet, related to algorithms and analysis, average case analysis of algorithms and so on, engineering, in physics, in number theory, the Ziegler G functions, they are definite functions also. So let's give a few examples of why it is so important and so useful. For example, if you want to prove such an identity, in which way to do it? What you have, when I say that a definite function is satisfying differential equations, if I am extracting the coefficient of the differential equations, I will get a recurrence for the coefficients. So to say that the coefficients are satisfying a linear recurrence with coefficients which are some polynomials in n, this is exactly the same as saying that the generating function is satisfying the differential equation with coefficients which are polynomial in z. Okay, so in which way to prove this? Well, the binomial coefficients, they satisfy a recurrence. Okay, this one also. The square of something which is satisfying a recurrence, you can compute a new recurrence for it. So, and you can compute a recurrence for the product of two stuff satisfying a recurrence. You have some algorithms, some automatic methods for this. And you can compute also the partial sums, the recurrence satisfied by the partial sums. And therefore, you get a recurrence for this left-hand side term. And here also, you have trivial recurrence for this and for the square. You get a recurrence also for the product. Oh, it is the same recurrence. You just have to check the initial conditions, and you get a proof that A equals B. And in fact, this idea is exactly the same everywhere. Here you have a product of Bessel functions. It's satisfying the differential equations. The product of two of them, you can compute the differential equations that they satisfy. The same for three of them, four of them, and so on. So you get some differential equation for this. When you do this infinite integral, you get some differential equations for the full product with respect to A, and you get a differential equation for this. Oh, it is the same differential equation. You check the initial conditions, and you get a proof that A equals B. And so you see, for most of the famous identities, you can play this game. Not only you can play this game, but it can even be given to a computer who will do it automatically. No need of human help. And in some cases, the recurrences is not the same, but you can factor it and check that the smaller factors they match. In some cases, it's you need one more step. But the same is working also if you do equations with finite differences or Q series and so on. This stuff could be then used to compute fast values of special functions. And also, in some cases, when you get some differential equations, some definite functions. So here is an example of a definite function. It's a solution of this equation. Finite linear differential equations with coefficients which are polynomial in C. When you get such an equation, you have also some tools to get the asymptotics of the coefficients. And also you get also, for example, some identities related to hypergeometric functions and so on. So it's very rich. It appears in a lot of different fields. And it is quite striking that the generating function of Ernst are definite. So if I take the generating function of the histories, in fact, if I consider the probability generating function of histories, it satisfies a linear differential equation of order 3 here, with coefficients which are polynomial in Z and in X parameter. So it's a little big equation, but you can see it fully here. Okay. And why we can be happy of such a stuff? Because it is saying something on the structure of the objects. It was not at all clear at first that these partial differential equations will be at the end one equation in just one variable. And as I said, it allows to prove then some identities related to it, to get the asymptotics, and also to allow some fast computations of the coefficients. And because of the fact that it is definite, for example, you can compute the coefficient Hn instead of running n times the evolution and checking all what happens. You have some algorithms which is traveling faster than the light, time traveling stuff. You can compute it in times square root of n. So it's not easy. It's an idea which goes back to the Chudovsky's for the class of definite functions. It's a kind of extension of the binary powering that you have for rational functions to the class of definite functions. So definite ions are definite. Okay, nice. But then what can we say about the asymptotics? So if we want to go the asymptotics of the distribution, we will consider the asymptotics of the moments. And to compute the moments, it's quite easy. It is just, in fact, computing the R derivatives, the derivative of order R, okay? And then I put x equals y, 1 into this, and it is giving me the factorial moments. Okay, and if I do this, the equation, then I can prove that the moments are behaving asymptotically like this. Okay, So the asymptotics of the moment, if I do this renormalization, it is this number. So natural question, is it the case that this quantity is the moment of some non-law? And is there just only one possible such law? Okay, so it's a classical moment problem. And for this, you have some theorems by Frechet and Shoah and by Perlman, which is allowing us to say that yes, the distribution of Young polyar urns is characterized by its moment. So the key stuff to check for this, and you have those conditions by Perlman, that you just have to consider the possible you consider the moment, there are asymptotics, you consider this quantity, you do the sum, and if it is diverging, then, okay, the genetic function, the moments are unique, the distribution is uniquely determined by the moments. Okay, and in fact, what we did for two different urns, at times even and odd, you can play exactly the same game with urns which are at times 1, 2, 3, 4 and P, okay? And then you get another distribution, which is a product of generalized gamma distribution times some beta functions, okay? So in one sense, what we saw up to now is that first, okay, you have these tools of analytic combinatorics using charting functions to get asymptotics and so on. Then you can apply this to polyar urns because their process is encoded by some differential equations, and you can use also charting functions to capture the exact enumeration on the asymptotics of it. And it is leading to some distributions which are those type of products of gamma, of generalized gamma distributions. And here, I find it fun to find in some book by Jung, Christian Jung, the Jung of Jung tableau, that after this, the reader who wishes to do so will have no difficulty in developing the theory of urns when they are regarded as differential operators. So you can check, there is a page, and in fact, I cheated a little bit. It's the sentence from the book where I just changed one word. So you can check it later, which word I changed. And here, it's exactly a sentence by Polya, which is that a method is a trick used twice. Okay, and therefore, now I will present you another method, another ingredient, which we will need to do more to go to Young tableau after. So now, one big part, the density methods. So what is this density methods? So you have some ancestors of it, which are related to work of Elkis, Pak, Barshnikov, Romik, and so on, which are playing with some, let's say, structures which are enumerated corresponding to posets, and therefore volumes of polytopes or type of stuff, and with some links with probability and enumeration. But I would say that we kind of digested a little bit more those ideas to transform it into some methods which allow some enumeration, random generation, and also some algorithms with respect to it. Okay, so you have a first application of it to some generalization of zigzag permutations by Philippe, and then to Young tableau in your work with Philippe and Michel. Alors, so let's give an example of what could be these methods on Young tableaus with some local decrease. So a Young tableau is a tableau in which the cells are increasing by line and by column. Okay, and you could have shapes which are not always rectangular shapes. So this is the definition of a Young tableau. But here, what we do, we allow some walls, the structures, which means that between those walls, we are breaking the rule that the cells should increase. They could increase or not. For example, here, okay, they don't increase, but between this and this, they increase, but they could not increase because of this one. Okay. So is there a way to enumerate these subjects and so on? So first, if you consider Tableau, so I have to go a little bit faster. So if you consider different type of constraint, you will see that it is leading to some nice formulas. Okay. Let me mention that is this one, which is that it is quite fun that when you put K walls, wherever they are, you get the same number of possible structures. It's an avatar of the famous Chung-Feller theorem in probability theory. Because you have some links with that is works here. Okay, and in full generality, you could have some big products formula related to some AKR formula and so on, but in generality for n by n, but for more general shapes, there is no clear formula. Okay, for example, for this shape, okay, you put some 2 by 3 shapes and you repeat them periodically. It's not at all clear what will be their generating functions. So you just have these 2 walls that you repeat periodically and you do a long strip like this. Okay, and if you do brute force, it is not at all working. But if you use the density methods, then you get a recurrence between objects of size n and objects in which you had one more n will be here 6 times n, and each n will be the number of rectangular blocks here. But if you add one more rectangular blocks, then you will get recurrence of this type. Okay, and this is just by following the volumes of the corresponding polytopes. And those volumes, you can consider them as integrals. And this, while you cannot find a clear generating function for this, you get a very fast way to compute the sequence. And this is very surprising, and it grows very fast. So brute force here, it would be completely impossible. And you will never have enough memory in your computer to get all these objects. So okay. So when I am saying that these objects could be seen as some type of polytopes and so on, it is instead of having numbers between 1 and the maximal, you can relabel them and so on, and then you will get a sequence of stuff of these types that you put like this, okay? And each of them, they have to satisfy this constraint. It is increasing by line, okay? Increasing 2 by 2 like this. But here and here, you have a wall, so you don't have any constraint between R and the value which will be below here. So the full set of constraints is captured by this polytope here. And so instead of having numbers, you put all the values between 0 and 1, okay? And then you can nest them. So if you start with filling some cells, then you get some type of conditional probabilities, which will be like a renormalization of the values to fill the next cells and so on. And when you do this, you get, when you compute this renormalization probabilities, which is done here, the constraint on the polytopes, that directly gives the integral that we had before. What's this one? Huh? This is the explanation of what is this integral. It is just the application of such a formula here. Okay. And well, you have some nice cancellation properties which are appearing here, which I don't have too much time to comment on. But the full idea is that thanks to these recurrences, it is allowing two stuff. First, you get some algorithms which can compute the sequence, but it also is giving you one way to make some uniform random generation, because you can generate the values, and then you know exactly by what to normalize these polynomials, which are given by some integrals, so that it will be the uniform distribution. So it's some efficient way, and it's the only efficient way that I know to generate such structures. Okay. So
Cyril,
yes,
can you resume in 4 minutes, please?
Yeah. So I go very fast now.
Thank you.
So now you should buy. It was a little bit fast, but you should buy that there is these density methods, and thanks to these density methods, then we can apply it to analyze the limit shape, the limit surface of Young tableau, and more precisely, we will analyze the value of this cell in the Young tableau of big size. So you consider triangular Young tableau with some slopes. Yeah, you have some slopes which is minus L over P here. Okay, and we want to analyze what is the value of this cell. And the value of this cell, in fact, so first, if you consider different shapes, here is what you can, the limit of the Young tableau that you can see. So the value of the cell is the altitude, and depending on the triangular shape that you have, it gives different limiting surfaces like this. And we are interested by the value of this cell here. Okay, so when you do this type of constructions of Young tableau of big sizes, you have already some known results. So first, it should be mentioned that you have different probabilistic models for Young tableau. You could consider the uniform distribution among tableaux with n cell, or you have also some other distributions like the Blanchard measure and so on, which would lead to, for sure, to different distribution of statistics. But however, what is known more or less on those objects is that the values in the middle of the Young tableau behave more or less like a Gaussian free field. That on the very border here, you have some stuff which are related to the Tracy-Widom distribution. So this is some work by Philippe Marshall. Here you have some local limit laws in this corner. And what we do in this work, we analyze how it is behaving in those corners. Okay. And to do this, in fact, it's possible to relate the Young tableau develop to some trees. And those trees, the evolution of these trees, it's possible to relate them to some polyar urns. And those polyar urns are exactly the ones that we saw in the first part. And therefore, the distribution of the corner in this Young tableau is given by this product of generals gamma. So knowing this corner, you even can say a little bit more on the Young tableau, the limit shape, because the distribution of the corner, you can make a red line here between all the values which are smaller than the value of the corner and larger. So you get a level line like this, a level line of the value of the corner. And the distribution, the fluctuation around this level line, it is exactly the fluctuation given by the product of generalized gamma distribution. And what is nice also is that you have also some natural relationship between the distribution in this corner and this corner, kind of duality if you want. And this duality between the corners is giving a probabilistic proof of the Gauss multiplication formula. It's a funny application of probability theory. Okay, so to summarize, to analyze the limiting landscape of Young tableau, and more precisely, the value in the corners, you have some links with some trees that you can prove via the density methods. So for this part, it was very fast and too fast. So if you want more, you will have to invite perhaps Philippe, who is there. Or and this evolution in the trees, you can capture it by models. Earned models, we know to handle them, historic genetic function, differential equations, and asymptotics of the moments, analytical matrix. It gives this product of general gamma distribution. It's very nice that they have a lot of miraculous properties. In fact, there are some of hypergeometric functions and more. You get some en passant for this work and gives this algorithms which allows to do some random generation. And for the distribution of the Young tableau, you have this duality between the corners, which are leading also to some funny factorization of distributions. So I will stop here, and if you have questions, they are warmly welcomed.
Thank you, Cyril, for this nice talk. If there are any questions, please, from the public. Are there any questions?
Oui, j'ai une question. Merci Cyril tout d'abord pour ton exposé. Alors, une petite question à propos de l'urne périodique. Donc, ce que j'arrive pas à bien comprendre, tu as dit que l'urne est P périodique. Donc, P périodique pour dire que P fois, on va changer la matrice de remplacement de l'urne, c'est ça. Donc, à l'étape 1, elle évolue suivant la matrice M1 jusqu'à à l'étape P, elle évolue suivant la matrice MP.
À l'étape P plus 1, elle va réévoluer la matrice M1, etc.
La matrice M1. Et à chaque, est-ce qu'il y a une relation entre les matrices MI ou bien tu as un choix particulier pour chaque matrice, ni suivant la
alors,
qui convient du tout, c'est ça?
Can you please answer in English, please?
Sorry.
Yes,
okay,
please.
okay.
That is appreciated. Thanks
Yes,
a lot.
for sure. Yes, I got tricked here. Okay, so the question was in the model here. Is there a link between M1, M2,
Yes.
or not? Alors, in the first part here, in fact, you could consider any M1, M2, MP, at least if they are balanced, positive entries and balanced. And then the method which I described will give you a way to access to the system of differential equations. You will be able to solve it and to get the nice limit laws and so on. Okay?
Yes. But in some diapos,
yes. Later in the talk, in the second part of the talk, then because of the exact problem which was considered,
yes.
It was M1 equals M2 equals M3.
Yes.
For the distribution of the corner in the Young tableau. Okay,
yes.
The results, the approach is more general than this, but for the application to Young tableau, you have this fact that M1 equals M2, and then just MP is a little bit different.
In this case, when the M1 is equal to M2, etc. What is the period?
MP is different. MP is not the same one as M1. So you have M1, M2, M3.
Okay.
And then if you want, you have M1, M1, M1.
And then
M1, M4, M1, M1, M4.
D'accord. It's okay. Thank you.
So the case of the set of matrices which are considered for Young tableau is just a subcase of the possibilities that we had in the first part.
And then you can't use Young tableau if M1 is different to M2 is different to M3.
So we don't use Young tableau. We don't use Young tableau to solve earned models. It's more the converse. We use earned models to solve a question on Young tableau. And if you do this, then you, for Young tableau, you consider a specific set of matrices. It's not any matrices for Young tableau. But in this approach, which is here, clearly you see you could have any stuff here. And here you clearly all these steps you can do them with a much more general. You get just a bigger system. You do the elimination and so on. And what is nice with the Young tableau, which is not easy to get directly, is this duality. The Young tableau is forcing some relationships between the limit laws. So the duality, which is also there, type of so on the Young tableau, if you inverse the slope or play with stuff like this, then you get some identities between distributions, limiting distributions, which are not clear a priori. And here it's quite funny because if you work directly on the Ernst, I don't know to prove this. For sure, it's always possible to prove it. But here you have a kind of direct insight of why it is the case. And just here I can say what you do on the Young tableau. For example, here you consider some you see it's shapes which are not always the same, but you repeat these shapes periodically. Okay, and now you consider another Young tableau in which, so this is the list of the shapes here, they are given here. And now put the last value, you put it first. And then you get another Young tableau, which is this one. And their limiting distribution is linked, and it is implying this type of identities. For more all of this, I think it's easier to go to the article. So Polya Ernst, very generic approach. Young tableau, more specific Ernst. But for sure, it's nice to have some results on Young tableau, even if the Ernsts are not more general there. But there is this cherry on the cake that the Young tableau give you for free some relationships and distributions for Ernst.
Other question, please. Other questions?
Okay. Assalamu alaikum, everyone, and happy Ramadan to everyone. This is Prateek. I had few questions, but I believe I'll go through the slides first before I make any assertions as of now. And I'm extremely sorry. Actually, there were a couple of them, and now I am having short of thoughts actually to assert or iterate my understanding of few things. So, and half knowledge is certainly bad. So I'll probably go through the slides first, and hopefully, thanks for your presentation, Professor. I really appreciate that. And I'm extremely sorry that I was late for the webinar. It's early morning here, and I believe there as well.
But if you have any question, even a question which seems perhaps naive, don't hesitate. Any question is welcome, no problem.
Yeah, definitely. Do you have any email that I can contact later, because I would want to delve into it. And,
yes. So I think that in the announcement that you get, there is a link to the seminar, and in the seminar there is a link to my webpage. So you can send me email whenever you want, no problem.
Awesome. Definitely, I'll look into that, and hopefully I'll also pick up some of the Arabic while coming to the class. Thank you.
Okay.
Take care.
Thank you. Other questions, please? The model where we choose from M1 to MP, not periodic. We have P matrix. And every time we choose with the probability 1 over P, one of these M matrix. It's not a periodic term, but...
It's not what we did. You are suggesting another model.
Yes. Yeah?
Are there interesting one?
Some links between periodic term and this model?
Yeah, yes, for sure. So it's a very natural extension. And for this, we can go back to this setting here, okay? In fact, even the functional equations, which are a little bit later, what you could do here, you could have here different, you have a lot of flexibility, which is possible. You could have even different, at the same time, you could have different matrices, and you put some probabilities between them.
Yes.
It will be some M1 with probability P1 and some M1 prime with some probability P1.
Okay.
Okay. And then what you do here, it will be exactly in this equation. You will add the two differential operators with some coefficients, which will be the probabilities. Okay.
Mm-hmm.
This step here is kind of automatic. There is no work, I would say, and it will work. And this step will work. What is not clear is what you will get after the elimination process here. Okay. And this, I would say, here, in this case, there is a little bit of some miracles which are appearing here. I don't know right now for which much more general model this miracle will still occur. Not clear, and very interesting question. For sure, it should be considered. So this is the first step which could differ. Okay. For example,
I'm sorry to interrupt you. So you were mentioning about probabilities. Probabilities of what, Professor? Exactly. What events are we trying to picturize through the probabilities? If you could reassert that.
So Rafik was suggesting that, for example, at each unit of time, instead of just having one matrix, you could have another matrix, M1 prime. Okay. And then you will pick one of these two matrices with some probabilities, some Bernoulli distribution or whatever. Okay. And I am saying that this is a very natural model, and you can completely capture it with this generative function approach. Okay. And it could be any periodicities and stuff. I would say that the level of generality that we can capture here is as long as you have, I would say, a finite set of matrices. So you could put some probabilities between the matrices. You could have some random entries. You could have periodicities. As soon as you have a finite set of matrices, okay, then you will get a finite system of equations here that you will be able to play with. Okay, so I would say that this is the natural level of generality. Okay, but not clear if it will still be definite, for example. This I don't know. This I don't know.
Okay.
Okay, so what I'm understanding as of now is initially to achieve the generality, we were computing through matrices like linear algebra, right? And in doing that, we are trying to address the problem I am not aware of, sorry about that. But what we are trying to achieve, then we want to convert in. So it is a deterministic approach, and the other one of probability, it's random approach. So how are we making that transaction from one approach to the other? I mean,
you have different level of probabilities. In the process which I described here, when I do the history, where are the probabilities?
Okay.
The probabilities
so
here you have just integers. Here, where are hidden the probabilities? The probabilities, they are hidden in when you do the full, where was the tree with the full set here, okay? Where are hidden the probability? Why is it a probabilistic process? Is because when you do at each unit of time, you sample one ball at random. Here you have some randomness. You pick one ball at random. And here, in one sense, what I am doing, I am writing at once all the possible list of possibilities with their multiplicity.
System of equations. Okay.
Yes. And if I divide I replace everything by 1 here, and I divide by this value, I get the probability distribution of each composition. So the probabilities, in fact, here it's enumerating the possibilities, but if you just divide by Hn of 1, 1, this, you get a probability distribution of the evolution of entanglements. So here it's one level of probability, okay? And this is what we analyzed in this talk, in this article. But Rafik was suggesting another level of probabilities, which is not picking the ball, but also picking the matrices. He was suggesting instead of always having this, to have another possibility of matrix, and we choose which matrix we use here. Okay, and I am claiming that all those models, they can be handled. Alors, they can be handled for up to 2 years. Okay, the next step, miracle or not, I don't know. And then it's not the end of the model, because you don't want to just to get the enumerations and so on, you want also to do the asymptotics. And then on the other, for more general models, you need to redo some work. You need to check what will be the asymptotics of the moments. It will be perhaps not always the case that the asymptotics will be such that it is uniquely determined by the moments, perhaps, not clear. So I will say that it's very easy to follow what we did, but I cannot predict where possibly you will have slight differences and need to do more work.
Thank you again.
It should be similar.
Thank you
again,
again,
I would
Cyril.
need to study better. Thanks for bringing that up. Appreciate that.
Pratik, I have sent you the email of Cyril by the chat.
Oh, very good.
Thank you again, Cyril, for this nice talk. Thank you for all the participants. And see you next week, inshallah.
Okay. Thanks, Rafik. Thanks, everybody.
Thank you, Cyril.
Okay.
Thank
Take
you.
care, everyone. Bye-bye.
Bye.
Bye-bye.